Today we are going to see about the economic load dispatch of n thermal generating units. That is formulation. The how the like your economic load dispatches get formulated. Okay, of thermal generating units. So why I'm insisting of only thermal in the sense already you know that reason why I'm insisting only on thermal generating units, because thermal generating units are very costly rather than other generating units. So other generating units, it's okay. If you are not doing economically, also the resource cost is very very less. But coming to the thermal generating units, you need to do very economically. Why? Because the cost incurred in thermal generating unit is much. Okay, it is of as I said, like per unit of coal, per kilogram of coal itself, like 12 rupees we are spending. 12 rupees at the large scale. At the large scale, uh, you may able to produce at 8 rupees. Okay, sometimes your union government is giving some like subsidy for that. Sometimes state government also taking something, some is spending some amount for that. Finally, at the end user, so we are the consumers. So what we are enjoying that part. End users, we are enjoying that part. So in that, okay, so if the cost is less, if the cost is less, automatically we are. But how they are managing? Because per unit of kilogram itself 8 rupees, and they are giving per unit for our, for domestic users, as only 5 rupees or 6 rupees at the maximum. How they are managing na, as I said, like subsidy, and as well as some companies, commercial tariff is more. Okay, commercial tariff is like 10 rupees, 8 rupees, then 12 rupees, like a commercial tariff 1, commercial tariff 2, commercial tariff 3, then industrial tariff. Industrial tariff, sometimes they are charging 15 rupees also, 20 rupees also at the extreme cases per unit itself. Why? Because their the electricity cost is directly proportional to their profit. Okay, because they will pay, that much amount. Why? Because their profit is more. Whereas if you take the domestic users like us, our profit, we are just consumers. Okay, like if you take in a day, we are daily consuming, not throughout the day. Maybe we are consuming some 12 hours, like that. In the morning hours, in daytime hours, very few load. Load is of very very few, like one fan, then one television, like that. One The load is of very very less. Whereas in the peak hours, like after 6 o'clock, if you take, we are spending more. Okay, we are consuming more power. All the appliances will be on, all the lights will be on, all the ceiling fans will be on, your ACs will be on. We are consuming the more. So here, in the thermal generating units, coming to the thermal generating units, heat is the major factor. Okay, so whatever the heat produced, that is directly proportional to your power, like you are accepting or not. Like whatever the heat based on the boiler heat. Okay, so whatever the heat we are giving to boiler, the same is directly proportional to whatever the power produced. Say, for example, we are reducing the heat from the boiler. We are reducing the heat from the boiler, means automatically the power production also will be reducing. So, more the heat, more the power production. So now we are going to formulate the heat rate characteristics, and as well as fuel cost function. Okay, so how to form the heat rate characteristics? You already know heat rate, H is directly proportional to I squared R. Okay, H is directly proportional to I square. Okay, heat is directly proportional to, in a transmission line, heat is directly proportional to I square. Okay, so whatever the heat produced in the particular wire or steel wire, that is directly proportional to I square. So I squared is nothing but the flow of electron, that is current. Okay, current square. So now if you take like thermal generating units, so this heat is directly proportional to power. Okay, power generation, that is power square. So similarly, H is directly proportional to I square. Okay, so similarly here in thermal generating unit, H is directly proportional to P square, that is power square. Okay, so next at the constant interval of time, what is happening is, say for example, you are heating the boiler. Okay, at particular at first instant, the heat will be of very more, then the power production is more, and for some point of time, okay, the power generation also will be decreasing to P, and next it is further decreased to some constant value, something like that. It might be decreasing. So we can frame this heat characteristics as H is directly proportional to P squared plus P plus constant. Okay, so this we can frame. Okay, so for removing this proportionality constant, what we'll do, we'll introduce one constant. So say in a heat rate also, H is directly proportional to I square. So what we'll do, we'll remove this proportionality constant. What we'll do, we'll put the R as a constant, that is resistance as a constant in normal cases, in transmission line. Okay, steel wire concept. In that, what we'll do is we'll remove this for removing this constant, we will add R. Okay, similarly here, what we are doing is we are removing this proportionality constant. Okay, so to equal to, okay, so H is equal to, so we are adding the constant as A. Okay, AP square plus BP plus some constant or C. We can take this as constant as C. Okay, so AP square plus BP plus C. So here also one constant will be there. Here also the constant we can take it as C, where A, B and C are the fuel cost coefficients. Okay, where A, B and C are the fuel cost coefficients. Okay, we can take that A, B, C, that is constant value, as a fuel cost coefficients. Okay, so H is nothing but amount of the heat that is being generated in the thermal power plant. Okay, that you already know. A, B and C are the fuel cost coefficient. So next is for removing this proportionality constant. Okay, so for removing this proportionality how we can convert this heat rate into fuel cost. Okay, so heat rate we derived, now we derived as H is equal to AP square plus BP plus C. Okay, for now how we can find out the fuel cost from the heat rate. Okay, fuel cost characteristics from the heat rate characteristics. Okay, so fuel cost can be found out by F. Okay, fuel cost we can take that as F. Okay, so F is nothing but H into that particular fuel rupees. Okay, H into that particular rupees. Say for example, some notation we are going for rupees. In the sum notation we are taking it as dollars, like that. Okay, so here we are in India, we are following our currency here, Indian currency, as rupees. So we can take this value as rupees. Okay, or otherwise if you are doing the universal calculation. Okay, throughout the you are in some US or some other foreign countries, then you can go for the dollar calculation, that also correct. This rupees calculation also correct. Okay, so here we are taking that as rupees. Okay, rupees. So fuel cost F is equal to H into that particular rupees. As like a small calculation. Okay, so one chocolate cost is sorry, chocolate is 1 rupee means how it will cost for 10 like that. So it will multiply, no, like that. How to find the fuel cost? Na? F is equal to H into that particular rupees. So whatever the rupees, whatever the cost incurred in that particular generating unit. Okay, say for example, this is first generating unit. Take that as some 18 rupees, as I said. So fuel cost F is equal to H into that rupees. So here also you need to multiply. Here also you need to multiply this rupees here. Okay, rupees here. So you can find out the fuel cost characteristics. Okay, so here coming into the characteristics. Okay, coming into the heat rate characteristics or fuel cost characteristics. Okay, so here in this axis we are taking the heat rate as mbtu per hour. That is, mbtu is nothing but million British thermal unit. Okay, million British thermal unit. I think you have studied in your earlier classes, in your power system, then as well as in some other your physics, chemistry, and all. You might be coming across this unit. That is how we are calculating H. Okay, H in the million British thermal unit. Okay, per hour. Okay, so we are taking the heat in this axis and power. Okay, power generation, output power generation in this axis. So output power generation we are dealing with megawatt. Okay, so not a watt. Okay, why? Because if you take like any power plant, they can tell in megawatt only. So what is the capacity of power generation in the particular power plant? They will tell like 100 megawatt, 200 megawatt, 500 megawatt. Then if you take like thermal generating unit, they will say like 500 megawatt, 1000 megawatt, 1500, 2500, 2000, then 4500, like that. They may tell in megawatt. So we are also dealing with megawatt in the sense 10 to the power of 6, 10 to the power of 6 watts. So it is not a very easy task. That is, how many zeros? 10 to the power 6 zeros, 6 zeros watts. Okay, for generating 1 watt, 1 watt, how complex it is. So we are generating in megawatt. Okay, megawatt. So here in this axis we are taking the output power generation in megawatt. Okay, as the heat generation, as the heat generation in the boiler increases, automatically your power generation also will be increasing in the linear manner. Okay, so if you draw the characteristics, if you take the heat rate, some values. Okay, so some heat rate as some other 100 mbtu, 200 mbtu. So what is 100 mbtu? What is the power generation? Like that, if you mark now, so based on the amount of the heat generation. Okay, so it is also increasing in the linear manner. Okay, power generation also increasing in the linear manner. As I said, like minimum power generation also should be there, maximum power generation also should be there. Okay, you should not operate your power plant at a minimum as I said, like if you take like 100 megawatt, you should not operate below 80 megawatt. Okay, definitely it has to generate minimum 80 megawatt to the maximum of 100, means some plus or minus 5 percentage. Okay, so 105 or 110 megawatt. Okay, but they will not go like that. In extreme cases, sometimes the load might be increasing. In that scenario, little bit they will go. Okay, little bit, if the generation is 98 megawatt, even though that is 100 megawatt, the generation is around 98.5 or 99, like that. They may go up to 101, 102, 103, like that. So it will not, they will not cross that value also. Why? Because the lifetime of the generator also will be decreasing. Okay, so if you are purchasing a new generator even in your house, 1 kVA generator or a 1.5 kVA generator or a 2 kVA generator in your house. Okay, there is some maximum load. Okay, maximum load for that particular generator. Say for example 1 kVA. Okay, together like five tube lights or five LED lights, then some three fans, then one television, like that. If you calculate, you are having approximately a load of 1 kilowatt, 1 kilo watt amperes. Okay, 1 kVA. So what you are doing is, you are purchasing a diesel generator. Okay, so what you are doing is, you're going to on all the loads in the load in the particular in your house, and you're going to on the generator. Okay, so generator will not able to tackle that load. The speed also is reducing. If you calculate the efficiency, sometimes your lights also, it is coming down and going up, coming down and going up. Your fans also, it is rotating in first thing as first cycle will be like some 500 rpm, another 800, another again 400, like that. It is coming down and going up, coming down and going up, like that. So okay, you can't tolerate, you're overburdening. Okay, you are overburden that particular generator. Okay, so overburden also, it is if you overburden like that, okay, I think you can use very for few minutes, maybe so 1 minute 2 minutes you can use. Okay, so in a Xerox shop, in a photocopy, if you go now, in the power shutdown time, what they will do, they will on the generator for only the Xerox machine alone. Okay, Xerox machine alone. They will off all the loads. So only the Xerox machine only will be running. So immediately, quickly they will take. Why? Because that the Xerox machine of load, if you take like 2 kVA, 4 kVA, like that. Okay, so they will be also having like a 5 kVA generator. Okay, so what they will do is, and also diesel cost, diesel cost also like 100 rupees, more than 100 rupees. So what they will do is, as soon as possible, they will take the Xerox, and then they will shut off like that. So like optimizing the fuel and also optimizing the usage. Okay, so if you overburden that, the lifetime. So in the nameplate, if you are buying a generator, they will be giving some warranty period. This generator can work up to 10 years, like that. So this is a warranty we are giving. If you are overburden that generator, so the lifetime, automatically lifetime of the generator also will be decreasing, decreasing to decrease to some other values. Okay, it will be very very less. So in that scenario, what ultimate loser is ourselves only. Okay, instead of coming 10 years, it will be only run for only 2 years or 3 years. Okay, so again you need to purchase a new generator. Okay, 1 kVA generator is somewhat 30,000-40,000, so you can easily buy and replace. But if you go in megawatt, 100 megawatt, 500 megawatt generator, 1000 megawatt generator, okay, if you are overburdening the generator, okay, for many time, very few time, 1 or 2 megawatt, 3 megawatt, you can increase. The tolerance limit will be there. Okay, so even though that efficiency will be little bit getting reduced, but the even though the tolerance limit is there, you can generate. But in the large scale, if you generate like that, so definitely you need to replace. So that will be in crores. Okay, that the generator will be in crores and crores of rupees. Replacing that also will be very costly. So that also we have to take that into account. So if you take instead of heat rate, if you take the fuel cost. Okay, so fuel cost, what is the unit? Rupees per hour. Okay, rupees per hour or dollar per hour. Okay, so either you can use our currency or otherwise general currency, dollar. Okay, dollar per hour. So dollar is followed universally. Why? Because if you want to buy crude oil, so what they are doing is they are buying in dollars. Majority of the countries, majority of the countries, they are buying in only dollars. So universally, if you go for the fuel cost, they will be calculating in dollar only. So after dollar, we can convert that to our Indian units, or otherwise, if the Indian units itself are available, then you can easily take that value also. Okay, so what I'm doing is, if I'm taking the fuel cost in the same axis, okay, same axis, rupees per hour, and power generation in megawatt, okay, so that is in this axis. So the characteristics will be same only. Why? Because like if you are spending more fuel, okay, more fuel, automatically the power generation also will be increasing linearly. Okay, so if you are spending less fuel, so this characteristics will be coming like this, it will be going like this. Okay, but if it is going like this, that is of no use. Okay, power generation is the major factor. Okay, so as far as fuel cost, we are increasing, so automatically our power generation also increasing in a linear manner. Okay, so subject to, so minimum and maximum operating limits. Okay, there is some minimum and for every generator, 100 megawatt, 500 megawatt, 1000 megawatt, as some minimum and maximum limits also will be there. Okay, so now what I am doing is, I am going to consider two generating units. Okay, two generating units. So first generator, I'm taking it as F1. F1 of P1 is equal to A1 P1 square plus B1 P1 plus C1, that is rupees per hour. Okay, so fuel cost, the unit is rupees per hour. Okay, then second generator, if we take the second generator, F2 of P2 is equal to A2 P2 square plus B2 P2 plus C2. Same. Okay, this coefficient only will be changing. So based on this coefficient, the power generation also P2 square here. So then P2 plus C2. Okay, so similar. So general formulation is Fi of Pi. Okay, general formulation is Fi of Pi is equal to Ai Pi square plus Bi Pi plus Ci, where I is equal to 1 to n. Okay, so if you combine, okay, I want to combine this now. What I need to do is, I need to add this, that is F of P1, that is total fuel cost. I'm going to find out the total fuel cost F of P1. Okay, so it's nothing but F1 of P1 plus F2 of P2. Okay, F1 of P1 plus F2 of P2. So this value plus this value. Okay, say for example, 5 generators are there, so 5 fuel cost function is there, so you need to add 5 fuel cost. Okay, for example, I'm telling. Okay, so here I have taken only two generating units. So F1 of P1 plus F2 of P2. So in general, how to write this? F of P is equal to summation I is equal to 1 to n Fi of Pa, where I is equal to 1 to n. Okay, I is equal to 1, 2, 3, 4. Say for example, n is equal to 5. Okay, capital N is nothing but 5. So N is nothing but number of generating units. Yeah, number of generating unit. Okay, so this F, so F5 of P. So we need to substitute 1, 2, 3 like that. So first is F1 of P1 plus F2 of P2 plus F3 of P3. So up to Fi of Pa. Okay, like that we need to add the fuel cost of all the like generators. Okay, fuel cost of all the generators, where this Ai, Bi and Ci are the fuel cost coefficients, fuel cost coefficients of the fuel. So what is our ultimate objective of economic load dispatch? So ultimate objective of economic load dispatch is to minimize this total fuel cost. So okay, so we need to minimize this total fuel cost, okay, incurred in all the generators. So then only, if we minimizing the fuel cost, as I said, total cost minimized for thermal power station. So automatically, as a whole, if you calculate, for a particular state, for where you're living. So in the particular state, if you take the all the thermal generators and you're calculating the fuel cost, so for this much fuel, we are generating this much power. Okay, even though maintenance cost is there, but a little bit you can add that maintenance cost also. But overall, fuel is playing very major part. Okay, fuel is playing very major part. Without that fuel, power generation also not possible. Okay, so if you are taking all the generators, and what we are doing is we are selecting the very least cost generators. Okay, so whichever the generation, like coal, cost is very less. Okay, for the thermal power plant, so that only we are selecting, and we are going for the generation. So automatically the overall cost, okay, overall cost, we are minimizing the total fuel cost incurred in all the thermal generating units. So automatically the overall cost will be reducing. Overall cost will be reducing. So that is our major objective function of your economic load dispatch.